Hello everyone, welcome to my channel Boring Physics. Today we are going to discuss about the second chapter, work power energy. Already the first part we have discussed in the part 1, that is work and power. So today we are going to discuss about the energy part. Today we'll discuss. So please everyone subscribe my channel Boring Physics. Now we are going to start the chapter, the exercise. Basically this is the second part of this chapter, that is energy. So first of all we have to know what is energy. What is energy? Energy is basically capacity to do the work. So capacity to do the work is called energy. Here we can say that capacity to do the work means a body capable of doing work. It will possess some amount of energy, that is called the energy. Now when we have to do some work, we need the energy. We can see that whenever we are having the food, any packaging food or anything, on that time there is written one that this one is this much kilocalorie. Suppose one chocolate, over there also you can see that calorie or kilocalorie, this things is there. So this one is giving basically the energy. Okay, so here energy is also a scalar quantity. Keep it in your mind, it's a scalar quantity. Scalar quantity. We can say that. What about the units of energy? Keep it in your mind, important units of energy. In SI system it should be joule, and in CGS system it will be arc. So basically work and energy both are having the same thing, means work and energy units both are same, because their dimensions also same. In CGS unit you can say it should be arc, denoted as arc. Okay, next part, whenever we have to discuss this thing, types of energy, the next topic we are having, that is called types of energy. Types of energy. What are the types of energy? Number one, we can say that the potential energy. Potential energy. And number two is called kinetic energy. Kinetic energy. What is called the potential energy? So first of all we have to know regarding the potential energy. Potential energy. What is potential energy? Basically we can say the energy possessed by a body at the position of rest. So what we can say, the energy possessed by a body at rest due to its position or size and shape. is called potential energy. I'm writing the term, that is P. Potential energy is denoted as U, capital U. You can say that this is the symbol of potential energy. Suppose any body is rest in its position. Suppose a book lying on the table. So that book have some potential energy. The book have potential energy. This potential energy we are having the two types. So the potential energy, basically we are having the two types. One we can say gravitational potential energy. Gravitational potential energy. And another one is known as elastic potential energy. Elastic potential energy. Okay. Now we can say that what is called the gravitational potential energy. What is called gravitation gravitational potential energy. You can see that the potential energy I'm writing that the PE, okay, possessed by possessed by a body due to the force of attraction, due to the force of attraction, due to the force of attraction of the earth, of the earth on it, is called gravitational potential energy. Same way we are having the second part, that is called elastic potential energy. What is called the elastic potential? Elasticity means the body have some elastic property. So means whenever the energy, we can say that potential energy, it should be possessed. Acha, I'm writing over here the potential energy possessed by a body, possessed by a body in the deformed state, in deformed state, in deformed state, due to due to change in its shape or size, due to change in its shape or size, is called elastic potential energy. Now the question, how we can calculate the gravitational potential energy? So these are the two potential energy we are getting, gravitational potential energy and elastic potential energy. So mainly always we are calculating this one only, that the gravitational potential energy. How we have to calculate? Suppose if we say one body we are having, one body whose mass is m, mass m, body we have to lift a certain height from the ground. Suppose this one is the ground. So now body we have to lift from ground to a certain point here. Means suppose to at A, we have to lift the body. What about the height of the body from the ground? Suppose we are taking h. Mass of the body already we know, m. So in this case, whenever we have to lift the body, we have to do some work basically. So the work W equal to, we know that, force into displacement, F into S. So here force equal to, we can say that force is mass into acceleration. Mass, now body we have to lift it up at a certain point. So acceleration means here it should be acceleration due to gravity. So we can say m into g into s is the, what about the distance we have taken, that is height. So we can write the formula W equal to mgh. So this is the work done to lifting a body up. So obviously whenever we are lifting the body, we have to store in the body in the form of its gravitational potential energy. So we can say that the same way, what about the gravitational potential energy? Gravitational potential energy for this body, for this body is equal to mgh. So that one is gravitational potential energy, already we are denoting as u. So we can write that u equal to mgh. Please keep it in your mind, the important formula will need this one. In case of gravity potential energy, we are having this much of things, so please go through this part. Sometimes whenever we are discussing that the gravitational potential energy, sometimes you need to calculate that the gravitational potential energy change. Suppose when the body can falls down from a certain height to another height, means suppose if we say uh, suppose if we say at first the body is in this position, this is the ground, suppose this one is the ground. Okay, okay. Now in this case, suppose body falls down at position A, the body is having, the body falls down to position B. Fine. So what about the height of the body at a point A from the ground? This height is, suppose we are taking, that is h1. And from B to the ground, what about the height we are taking, suppose h2. Okay. Now the body mass of the body, suppose I am taking m. Now body falls from a height. So from h1 to h2 height, body falls. So what will be the loss of potential energy? So here obviously the potential energy loss. So we can say the potential energy at A, it will be mgh1. Now another one thing, the potential energy at B, it should be mgh2, right? Now which point potential energy is greater? Obviously this one, because mass is same, g is same, so h1 is more. See, h1 is the whole part, h2 is the this much of part. So obviously potential energy at A, it should be much more. So when the body is coming from A to B, we can say that there will be loss in potential energy. So loss in potential energy will become mgh1 minus mgh2. So we can say that mg we can take common, it will be h1 minus h2. So mg into h1 minus h2, that will be the loss in potential energy. I think clear everyone how to calculate. Sometimes we have to calculate the gain in potential energy also. In this case also we can say Suppose if we say that we have the body at first at B point. Acha, another one way we can say, another one diagram we can do. Suppose this one is the ground, this is the ground. Suppose we are telling that body is at a height, body is in this position. Body mass is same, m only. Body is in this position. Okay. What about the height? Height of the body, suppose we are taking h1. Now we are lifting the body in this position. So we are lifting from A to B. We are lifting the body from A to B. So this one is h1, and what about the height? This one is h2. Now we are lifting the body from A to B. So here will be gain in potential energy because height is increasing. So we can calculate here the potential energy at A. How much? We can easily say m is the mass of the body. M is the mass of the body. G is acceleration due to gravity. And at A means h1. Now if we calculate the potential energy at B, how much it is? Mg h2, because height, whose height is greater? H2 is greater. So what will be the gain in potential energy? If we have to calculate the gain in potential energy, it will be highest potential energy is this one, mgh2 minus mgh1. So what we can write? We can write mg into h2 minus h1, right? So this is very very important topic of energy. Now we are going to discuss about the kinetic energy. In between, if anyone have any doubt regarding this chapter, you can ask me in the comment section. I'll give you the reply. If you have any question, if you have any numerical problem, you just send it to me. No issues. So we'll do that the kinetic energy. What is called the kinetic energy? Kinetic energy just opposite of the potential energy. Potential energy, we have seen that body is at rest position, but here body should not be in the rest position. Body will be in the state of motion. So what we can say, what is the kinetic energy? We can say that the energy, so the energy possessed by a body, possessed by a body due to its due to its state of motion, state of motion is called kinetic energy, is called kinetic energy, means Ke, we can say. Now you have to see, we have to calculate, or you have to prove, or the calculation of the kinetic energy formula. Let's see first. So now we are going to calculate the kinetic energy formula. Let's see. Suppose we are taking a body. Suppose we are having a body, this one. It is moving in this direction. Body mass is m. Okay. Now suppose when the body is moving, body mass is, body mass we are taking m. So when the body is moving, obviously body should have some velocity. Suppose the velocity we are taking v. So velocity of the body we are taking as v. Now when the body is moving in this direction, so one opposing force, it should be applied on the body. So we can say that suppose the opposing force is F. Opposing force is F. Why? Because when the body is moving in this direction, so suppose after some time body comes to the rest position. Suppose in this point body comes to rest position. Here is a rest position. So when the body comes to the rest position at the initial, and the initial velocity was v, so we have to apply some force. Suppose we are taking the opposing force is F to stop the body at a certain position. So when we are applying some force, obviously there will be some retardation, there will be not the acceleration. So suppose the retardation we are taking, retardation is A, uniform retardation. Now when body starts moving from position A and body comes to the rest position at B, now how much distance occur by the body? Suppose we are taking the distance occur is S. So how much distance occur? We are writing distance occur, that is S. Distance occur by the body. Fine. We know that force equal to, we know force equal to mass into acceleration. So here there is no acceleration, we are having the retardation. So we can say mass m into the retardation, that is A. Keep it in a box. So F equal to mass into A. We are writing. Fine. Now if we say how much work done by this retarding force, and for that how much displacement occur, that is S. So how much kinetic energy produced by the body? Let's see. We can say the kinetic energy is equal to retarding force, retarding force into the displacement. So how much is the retarding force or the opposing force? We have no, retarding force is F into the displacement is S. Keep it in mind. So the kinetic energy formula we will calculate from here, that is K equal to F into S. This one give the equation number 1, this one give equation number 2. Now at the beginning body was moving with a velocity v, so means the initial velocity of the body, that is v, and finally body comes to be at the rest position, so the final velocity should become 0. So we can write the initial velocity u equal to v, and the final velocity v equal to, we can say that should become 0, because finally it has reaches to b position and it is stopped. So final velocity is v. Now one equation we know that in class 9 also we have done this equation, equation of motion, v square equal to u square plus twice as, right? Now in this case if we put the values, final velocity is 0, means v equal to 0, we can put 0 square, u equal to v, so v square plus twice as. Acha, here we know that there is a retardation. Retardation is always negative, so we can say minus a into s. So what we can say, v square minus 2as equal to 0. Now here we'll calculate. Already we know that F equal to M into A, we have got it from this relation, and S we need to calculate from here. So let's see. From here we can say V square equal to 2AS. So we can say S equal to V square by 2A. Now the question, when we have to calculate the kinetic energy. So the kinetic energy equal to, we can say, F into S. You can write from equation 2, F into S. From equation 1 we can calculate F equal to mass into acceleration. So write M into A into S. We have got it one formula, V square by 2A. So V square by 2 into A. So A will be cancelled out. We are getting mv square by 2, or you can write half mv square. So this one is the kinetic energy equation, that K equal to half mv square. Okay, this one is known as the kinetic energy. Clear everyone? What about the kinetic energy derivation? Like this way you can do it. The next topic which one we have, that is called the relationship between kinetic energy and momentum. Let's see. A relationship between kinetic energy and momentum. What is the relation between kinetic energy and momentum? Acha, momentum means, suppose we are taking a body mass is m, and body moving with the velocity is v. Now the momentum we can easily calculate. The momentum is denoted as p. So p equal to, we can say, m into v, means mv. And the kinetic energy formula, if we say, so the kinetic energy equal to, we know, half m v square. So one thing we can say from here, from the previous relation, we can calculate the value of v. So v equal to, we can write p by m. Keep it in your mind. So we have the formula, half kinetic energy means K equal to, we can say, half m v equal to p by m whole square. So we can write K equal to half into m into p square by m square. One cancel, so it should become m. So kinetic energy K equal to, we can say, half, or you can say, p square by 2m. That is only the relation K equal to p square by 2m. Or you can write p square equal to 2mk. That also you can write. This one is also correct. This one is also correct. Or from here, if you take p equal to, you can write root over of 2mk. That is also correct. So p equal to, if you write 2mk, that is also correct. So these are the basic derivation or the basic relation between the kinetic energy and momentum. Keep it in your mind, this one. One question can come, generally it is coming. Suppose any body, okay, suppose any two bodies we are having, one is very light body and another one is heavy body. Means which one is having the kinetic energy more, if the mass more, like this type of question it can come. Suppose we are taking the two body. One body A, that is a lightweight, light body, light body. Okay. And another one is body B. Which one is the heavy body? Heavy body. Body A and body B. Suppose body A having a mass small m. Okay. So what will be the kinetic energy? We can write that kinetic energy at A of body A, we can say that p square by 2m with respect to the momentum. Now here, suppose that the body B we are having, body B we can say mass is bigger body, heavy body, so mass is capital M. And what about the kinetic energy? We can say kb, it will come p square by 2 into capital M, right? Now if we compare whose kinetic energy is more, whose kinetic energy is more, so if we write ka by kb, if we want to calculate, what we'll get, p square by 2m divided by p square by 2 into capital M. So what will happen? We can say p square by 2m into 2 into capital M by p square. P square cancel out, 2 cancel out. We are getting capital M by small m. So means Ka equal to capital M, Kb equal to, we are getting that the small m. So whose mass is greater? Whose mass is greater? We can say that if already we know that mass is greater for B, but kinetic energy it should be greater for K is greater than Kb. Keep it in your mind. Okay. So whenever we have to see this one, please keep it in your mind. This will do. This one was, suppose we can say case 1 where p was constant, means the momentum was constant in this part. Now the second part, momentum will be, we can change, and there will be the kinetic energy will be same. Now the same thing, body A is the light body and body B is the heavy body. So same way, case 2 we are doing, where the kinetic energy is same. Kinetic energy is constant or same. Kinetic energy is constant. Now what we can say in this case, suppose if we calculate for the uh, light body we can say pa, that the momentum for a light body, what we'll get, we'll get root over of 2mk. Here kinetic energy is same for the both the cases. And for the heavy body we can say that momentum should be pb equal to, we can write root over of 2 capital M into k, right? Now what we can say in this case, if we compare this one, what we'll get, we'll get, suppose we can comparing pb by pa. So pb equal to root over of 2mk divided by root over of 2 small m k. So ultimately what we'll get, root over of capital M by small m, that is pb by pa. Now if we say, if here capital M is greater, we know that this is the heavy body, so capital M is greater than small m. So we can easily say, what about the momentum at heavy body, it should be greater than the momentum of a light body. Which one was different in the first case? First case when the momentum was same, here momentum was same, And the kinetic energy in this case, kinetic energy in the light body, it was much more than kinetic energy of the second body or the heavy body. So these are the differences. This type of question can come. Work energy theorem, very very important topic, please do that. Let's see. Work energy theorem. Work energy theorem. What is it? Work energy theorem. We can say that by the work energy theorem, we can say the work done, the work done by a force on a moving body, on a moving body in the same direction, in the same direction, in the same direction is equal to, is equal to the increase in its kinetic energy. Kinetic energy. So this is known as the work energy theorem. Work done by a force in a moving body in the same direction is equal to the increase in its kinetic energy. Please keep it in your mind, this part, increase in kinetic energy and work done. This is called the work energy theorem. These two part, please keep it in your mind. Work energy theorem. Now how we can prove it? Let's see. Suppose we are taking a body. Suppose we are taking a body of mass m. We are taking a body of mass m. We are taking. Fine. Now body have the initial velocity. So we are telling, suppose the initial velocity is u. U is the initial velocity. Now when we are applying a force on this body, so suppose, what about the force we are applying? Suppose applying force is equal to F. We are applying the force on that body, that is F. So when force will produce, already the initial velocity we are having, then we are applying some force on it. Then what will happen? It will accelerate. So what about the acceleration? Suppose we are writing acceleration of the body is, suppose we are taking A. So velocity from u, it has changing to v. So now the final velocity is v. Fine. Final velocity is v. So obviously when the initial velocity it was u, we have applied some force on it and it reaches to the final velocity. Obviously it has covered a certain distance. So how much distance covered? So covering distance, suppose I'm writing s. Covering distance is. Now we know that we have to calculate the work, right? So let's see. We know that work equal to what? We have to calculate the work done. So work done by the force. Work done by the force. That we can say W equal to, we know, force into displacement means F into S, right? And another one thing, force, so already we know that it will be mass into acceleration. We can easily calculate, or we can write also over here F equal to mass into acceleration. Mass is m, acceleration is a. But this displacement we have to calculate. How? We have done one relation previously, that v square equal to u square plus twice as, right? From here we have to calculate the value of s. How we can? We are taking v square minus u square equal to 2as. From there we can write v square minus u square by 2a equal to s. So s equal to, we can say that v square minus u square by 2a. Okay. Now we have to calculate the work done. Work done is w. W equal to, we can say, force into the displacement. Force equal to, already we know that, mass into acceleration into s. S equal to this one. We can say v square minus u square by 2a. So in this part, a we can cancel it out. So we can get half into m into v square minus u square. So half into v square mv square minus u square means we can write this one should be half m v square minus half m u square. So half m v square means kinetic energy at the final position minus, we can write kinetic energy at the initial position. So what about the total work done? W equal to, now we can say, kf minus ki, or what about the work done? It will be denoting as the increase in kinetic energy. Okay, kf minus ki. That is the work energy theorem. Please keep it in your mind. So from here we can write in one line that the work done W is equal to, we can say, increase in kinetic energy. Increase in kinetic energy. Okay. So this one is the proof of work energy theorem. Now we have to know how many types of kinetic energy we are having. Let's see how many types of kinetic energy. So give the heading first. Types of kinetic energy. Types of kinetic energy. What are the types? First one, we can say translational kinetic energy. We can say translational kinetic energy. Translational kinetic energy. What is this, that translational kinetic energy? Suppose the motion of a body in a straight line path. The motion of a body in a straight line path. So you can say motion of a body in a straight line path. In a straight line path. Straight line path. If you say for the example, you can say that suppose a car is moving in a straight line path. That's it. That is the translational kinetic energy. Number two, if we say number two, we are having a rotational kinetic energy. What is called the rotational kinetic energy? Let's see. Rotational kinetic energy. What is this rotational kinetic energy? When a body rotates about on its axis. When a body rotates about an axis. Rotates about an axis. This motion is called rotational kinetic energy. Now you can ask that what are the example? Suppose a rotating wheel, rotating a fan. So these are the examples of the rotational kinetic energy. Now the last one we are having for the kinetic energy, that is called vibrational kinetic energy. Let's see, number 3 is called vibrational kinetic energy. Vibrational kinetic energy. What is called the vibrational kinetic energy? Suppose if a body moves to and fro from its main position, any body, you can say what, any body moves to and fro, to and fro about its main position. Its main position. This type of motion is called, or this type of energy is called vibrational kinetic energy. If you say, for an example, suppose if we say one rubber band, both side it will be fixed. Now if we stuck in the middle, if we stuck in the middle, we'll get the vibrational kinetic energy. Okay, suppose if you say a wire clamped in the both sides, means both ends, if we stuck in the middle, we'll get that the, we can see that the vibration produce. So this type of motion can create the vibrational kinetic energy. So these are the examples of translational, rotational and vibrational kinetic energy. Now there is one question can come, what is the difference between kinetic energy and potential energy? The difference between kinetic energy and potential energy, what we can say regarding this? Suppose this one is the kinetic energy and this one is known as the potential energy. Suppose the first one, you can give the definition you can give both the cases. Number one is always the definition part, you can say. Okay, number two, you can say, in this case we can say the kinetic energy, it can depends on the velocity or the speed, we can say, because half mv square is the uh, kinetic energy formula is half mv square, so it can depends on v or the speed. And in this case we know that potential energy is mgh, so means it does not depend on the speed of the body. Okay, it can depends on the height of the body from the ground state. You can say that for the kinetic energy it can change into any other form it can change, any other form it can change, it can change. In this case you can say that number 3, it can change only in kinetic energy, means potential energy only changes to kinetic energy, nothing else. So this type of differences you can keep it in your mind, can come in the exam, that what are the differences between kinetic energy and the potential energy. Okay, if any problem, any question you are having, you can freely ask in the comment box. Follow my channel, subscribe my channel, you'll get all the chapter details in this video or the upcoming video, you will get everything. So please do subscribe. Okay, here one thing is there, that after this you'll get different forms of energy, different forms of energy, and there is the conversion of energy. Here you'll get different forms of energy, different forms of energy. Different forms of energy. Okay, different forms of energy means what we can say that in this case you will get that the solar energy, you will get heat energy, you can get heat energy, you can get light energy, chemical energy, light energy, you will get hydro energy, so many types of energy whatever you have, electrical energy, electrical energy, nuclear energy, magnetic energies, sound energy. Okay, nuclear energy, magnetic energy, sound energy, sound energy. Okay, wind energy. So these are the types of energy. Already we know about it. In previous class also we have done a bit. But in this part, what is the main thing? What is the important thing? If you say this one is known as the conversion of one form of energy to the other. That is very, very important. Question will come from this part. Please keep it in your mind. Conversion of energy. That is very, very important part. Conversion of energy. Different forms of energy, suppose any type of energy, they can say that what is called hydro energy. Hydro energy means whatever the energy possessed by the fast moving water, that is called the hydro energy. They can ask what is the electrical energy. Okay, so if two dry bodies are rubbed together, they get charged due to the movement of free electrons from one body to the another body, so that the electrical energy can be produced. Light energy, the form of energy in presence of which other objects we can see, that is called the light energy. Okay, so this type of, but most important one from this chapter, that is the conversion of energy. That is very, very important. Suppose if I say, give one example where mechanical energy converted to the electrical energy. Suppose if we say mechanical energy, mechanical converted to electrical. Give the example. Mechanical energy converted to the electrical energy. Example is known as dynamo. Dynamo is the example. Same way, if we say, if electrical energy changes to mechanical energy, that is called motor. Electric motor. Electric motor. So this type of conversion of energy it can, suppose if I say the electrical energy changes to the sound energy, that is very, very important one, and the students are doing also so many times the wrong thing. Electrical to sound, electrical to sound energy is the example. If you say that is the loudspeaker, you can say loudspeaker. Loudspeaker. If we say just vice versa, means sound energy to electrical energy, sound to electrical energy, what is that? You can say microphone. Many students are confused about it. Okay, so please, whenever you'll do this part, keep it in your mind, and in the exam hall also it can come. That give one example where the mechanical energy changes to electrical energy, electrical energy changes to sound energy, or vice versa. It can. Same way, if they ask that the chemical energy changes to the light energy, chemical to the light energy. Important part, chemical to light. If you say, we can say that the candle, candle, candle means obviously candle should be lightened. So you can say that the lightened candle, lightened candle. Okay. If you say that light energy to chemical energy, that is very, very easy one. Already we know that light energy to the chemical energy, what? In biology, we have done this part that is called photosynthesis. 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 Okay, so these are the examples they can give. Okay, in the exam, they can give also that suppose they say that in microphone, what are the energy conversion can be possible. This type of also question can come. Suppose if I say electrical to light energy, electrical to light, electrical to light, what will be? Obviously, electric bulb. We can easily say that is the most easy example. Electric bulb. But if we say the light energy to the electrical energy, light energy to electrical energy, it will be a photo cell. Photo cell, you can say. So these are the examples of the conversion of energy. Please keep it in your mind. This type of question can come in the exam. So go through this part very, very minutely. Please do that properly. And the next topic, which one we have, that is the conservation of energy. Let's see that the last part of this chapter we have to do, that is called conservation of energy. Conservation of energy. Conservation of energy. Conservation of energy. So by the principle of conservation of energy, we can say that energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed, nor can be destroyed. Destroyed. It only change. It only change from one form, one form to another. So conservation of energy principle is energy can neither be created nor can be destroyed. It can only change from one form to another. Okay, so this is the conservation of energy. Here interchange can be possible. Suppose if we say interchange between the potential and the kinetic energy possible, but what about the total energy? It should be constant. So means total mechanical energy of a system, it should be constant. Now you have to see the verification of uh, total energy of a body, it should be constant. Total energy means either kinetic and the potential, means we can say that in one word, that should be the mechanical energy, right? So let's see first. Theoretical verification. Verification of kinetic energy plus potential energy equal to constant, equal to constant for a free falling body. For a free falling body, suppose we are taking a body mass is m, a small body mass we are taking small m. Okay, the body is feeling freely, the body is falling freely under the gravity. from a certain height. So now, suppose we can say here is the body first, the first position of the body we are keeping there. Okay. Now, this position, suppose I am telling A. Okay. Here is the ground. This is the ground. Now, at this position A, we have to calculate the potential and the kinetic energy. Fine. Now, the body is freely falling in between any one position we are taking. Suppose in this position. This position is B. Okay. Now the body is coming to the ground, that is at C. So the three positions of the body we have mentioned. We have mentioned. Now, suppose the body is falling from a height h. Body is falling from a height h. Means at A position, what about the height of the body from the ground? That is h. Okay. Now we'll calculate the kinetic and potential energy at a point, and when it has fallen at a distance x, we'll calculate another one time the kinetic and potential energy, and at the point C we'll calculate the kinetic and potential energy, and we'll check that the total energy should be same or not. So A to B, at this distance we are taking x, means A to B, this distance. So obviously we can say B to C, this distance should be h minus x, because this whole distance already we have taken, that is h, and the B position from A, that is the x distance. So obviously B to C, it will be h minus x. Okay. Now we are going to calculate what about the total energy at the position E. Body mass m, already I told. So now first we are going to calculate at position A what will be the total energy at A. Let's see. First one, the kinetic energy. How much? At the position A, body is in rest. So body not in motion. So kinetic energy, there will be no kinetic energy. So it will become 0. At A, what will be the potential energy? Potential energy means we can say mass is m, body is on that position, a fraction of time we can say body is at rest. So potential energy, we can say that it will become mass into acceleration due to gravity into h. So potential energy is coming mgh. Potential energy, you can put that u also, there is no problem. Okay. So the total energy, so the total energy, it should be equal to kinetic energy k. I have written ke, so ke plus pe, it should become 0 plus mgh. So it will become only mgh, right? So this is at A. Now we are going to calculate at the position B. Now let's see. At B, what will be the kinetic energy? Before that, we have to know, whenever the body is coming from A to B, so body should have some velocity, right? Suppose we are taking the velocity is the velocity acquired by the body, acquired by the body. Suppose I am taking v dashed. Okay. Initially body was in rest, so obviously u should become 0. So we can say u should become 0. Body comes to the position at b. B means what about the distance covered? S equal to, we can say, x. And what about the acceleration? Acceleration means we can say acceleration due to gravity, right? Now we are going to calculate the velocity. Velocity, one formula we have done, that v square equal to u square plus twice as. By this formula we can say v equal to v dashed square equal to u means 0 square plus 2 into a means g, acceleration due to gravity, into s is the distance, that is x. So means we can say v dashed square equal to 2gx. Okay, now we have to calculate the kinetic energy. Let's see. So the kinetic energy equal to, we can say, half m v dashed square. So what we'll get? Half into m into 2gx. So 2 will be cancelled out. What we are getting? We are getting mgx. Fine. Now we have to calculate the potential energy. Now see, potential energy at b, what will happen? From the ground, what will be the distance? That is h minus x, right? So we can calculate the potential energy at b. So the potential energy will be how much? Mgh. So mg into, here it will be, height will be h minus x, because b point from the ground, b point from the ground, we can easily calculate that it should be h minus x. So we can write mg into h minus x. So what we'll get? We'll get mgh minus mgx. So what will be the total energy? So the total energy equal to kinetic energy plus potential energy. Kinetic energy is mgx plus potential energy is mgh minus mgx equal to, we can say, mgh. So what about the total energy? That is mgh. So at A position, we have got the total energy is mgh. At B position also we are getting mgh. Now the last one, it is left, that is at C. If we can calculate here, it should be better. No, okay. We'll calculate here at point C. At C, what will be the total energy? Now see, what will be the velocity acquired by the body to reach at the ground C? Suppose when the body reaches to C position, this position, we have to calculate. Acha, initial velocity was not there. Means at the beginning it was at rest. So initial velocity u equal to 0. How much height it has covered? That the total height, that is h. And what about the total? What about the acceleration? That should be g only. We can easily say. So in this point, there will be no potential energy because there is no height. Ball already touches the ground. So there will be no potential energy. But kinetic energy will be acquired by the body to come from A to C. Now let's see first how we can calculate. So initially u equal to, we can say that initial velocity it was 0. How much displacement covered by the body? S equal to, we can say, h. And acceleration is equal to acceleration due to gravity, that is g. We know that the equation, that is v square equal to u square plus twice as, right? So we know that v square equal to u is 0 plus 2, a is g because acceleration due to gravity, and s equal to h means 2gh. So here the kinetic energy we can say the kinetic energy equal to half m v square. So equal to, we can say, half m v square is 2gh. So 2 to cancel out, we are getting mgh. That is the kinetic energy. If we say about the potential energy, already we have seen when the body comes to at sea, means it touches the ground, so there will be no height or no distance from the ground. So we can easily say that potential energy should become mgh, means mg into, there is no height, height is 0, so basically the potential energy will become 0 only. So what will be the total energy? So the total energy will become mgh plus 0. It should become also mgh. So ultimately one thing it has come, at the three positions A, B and C, always the total energy is mgh. At C, at B also mgh, and here you can see at A it was also mgh. So ultimately we can say that the total energy is constant. So we can say the total energy at any point, total energy at any point is constant. Okay, please keep it in your mind, important topic of this chapter. So now here we have to make a graph, and we have to plot the potential and the kinetic energy graph with respect to the height. Okay, so let's see first. We have got it in the three positions. We have calculated the kinetic and the potential energy. So along x-axis we'll put height. Here the three heights we'll consider. First one is at point A, we'll do. Next one we'll do at B, and the third option or the third point we'll take at C. And along y-axis we'll put the energy. Energy means the total energy we'll put. Okay, so energy highest position we have got it, that is mgh. Suppose we are taking here mgh, and obviously the midpoint we are taking mgh by 2, or we can say that the half mgh. Fine. Now we are going to at the position, at first position at A. If we see that the position at A, kinetic energy was 0 and potential energy was mgh. Fine. And the total energy was 0 only, right? So suppose if we see that at the first position kinetic energy was, at position A kinetic energy was 0. So here first we will plot that the kinetic energy. We have seen the three positions A, B and C, and we have the energy both kinetic and potential. Potential is U and kinetic energy K I am writing. Okay, so at A kinetic energy was 0, potential energy was mgh, right? At A, at the middle, means if we take this one is the middle, so we can say that over there the kinetic energy was half mgh, half mgh, and this one also it will be half mgh. And if we say at the position C, if you check kinetic energy, it was At the ground C, kinetic energy it was mgh, and the potential energy it was 0, right? Now both the cases we can see, one is the downward motion and another one is the upward motion, both we can see. And if we add them, we'll get that the mgh each and every cases, each and every point we'll get that only. Now first, suppose if we put that the kinetic energy, so kinetic energy at A it was 0, okay. At B it was half mgh, so I'm putting here the point. And at C it was 0, it is 0 only. No, sorry, at C it is mgh, so at mgh means this point. So kinetic energy it will be graph, it will be like this, it will be like this. That is the kinetic energy graph, ke. Now we are going to calculate, or we are going to write the potential energy. Potential energy, if we see, at first at C it was 0, so at C it is 0. Now at B it is mgh, so at B I am taking, it is mgh. And at A it is, sorry, at B it was half mgh, same only. And at A potential energy was mgh, so at A it will be mgh. So if we see, this line is the total energy, so the potential energy also at A it will become mgh. So this graph is pe, we can say that potential energy. And this height if we take from here, it should be at B, it should be h by 2 at a height. So this is the graph we can say. If you take that the upward or downward motion, you can easily see that each and every point, see at B kinetic energy 0, but at A kinetic energy is 0, but the potential energy is mgh, so total it will become mgh. If we consider at B point, over there kinetic and potential both are the same only, half mgh, half mgh, you will get same. At position C if we see, the potential energy is 0, but the kinetic energy is mgh, so total energy mgh, it will be constant only, okay. So keep it in your mind, this is one of the important things to know, please keep it in your mind. So this way we have seen that the conservation of energy, there is some application you can see also in case of the simple pendulum. Already we know that in case of simple pendulum, basically what is going on for the principle of conservation of energy. Let's see first that the conservation of energy of energy to a simple pendulum. Okay, so suppose basically we are having a simple pendulum, we know that how it is looks like. Here is one string, that is the mean position. If we say that, suppose this is for the ground one, okay. Three position we'll choose, this is at A, this one we can say at, suppose at the position, another one, these two are the extreme position, and this is another one position. Okay, this position is, suppose I'm taking as B, and this position we are taking as C. Okay, so it is swinging like this way. Okay, this is the mean position at A position. That is the mean position. Mean position means in this position, at the initial stage it will be at rest. So at rest means at A we can say that the potential energy will become zero because it touches the surface, so there is no height. So over here potential energy should become zero. If we say what about the kinetic energy, so in this case kinetic energy we'll calculate later on. Suppose at the extreme end, at the position B, when it will reach at the end position on that time, means the extreme end position, both the side means B and C also, both the side, for a fraction of time also there is a potential energy should be there, because there is a certain height from the ground or from the surface, height is there. So in this case we can easily calculate the potential energy equal to mgh. Okay, so obviously at that time potential energy is mgh, so kinetic energy should become zero over there. Now at the intermediate position, means between A and B and between A and C, the bob has both the kinetic and the potential energy. In this case the potential energy, when it is moving from the bob, it is moving from B to A, the potential energy changes to the kinetic energy, and at the mid position we can say here the kinetic energy should become mgh. Now again when it will reach to the C position, over there potential energy means kinetic energy at the end, where it will be for a fraction of time it will be in the rest position, over there potential energy will be mgh. So obviously the kinetic energy will become zero. So we can say that at A point potential energy is zero, kinetic energy we are getting mgh. So the total energy, so the total energy is mgh if we add them. At B, if we calculate, potential energy is mgh and kinetic energy is zero. So the total energy equal to mgh. At C, if we calculate, potential energy is mgh because both are the same only in this case, and the kinetic energy is zero. So the total energy will become mgh. Total energy will be mgh. So this is the conservation, means the application of conservation of energy to a simple pendulum we have discussed. In this chapter, means the energy chapter, work power energy, we are having this one, the part 2. This is the complete of the second chapter of class 10. Next day we'll discuss some numericals in the part 3 of this video. We'll do some numericals from this chapter, the important numericals we can discuss. If you have any question, any doubt, you can write the comments in the comment section. I'll give you the reply. Please subscribe my channel, Boarding Physics. Thank you all.